What happens when our most advanced space monitoring technology captures an image that, just totally defies explanation, only for the data feed to be severed at that precise moment? On June 18th, NASA's live stream tracking 3I Atlas, our solar system's third interstellar guest, transmitted a single, baffling frame. It showed an object with characteristics that appeared honestly, unnervingly artificial, then nothing but static. The official report cited network failure, but cryptographically verified data from independent archivists confirms the image is real. So what was that razor-sharp glint in the void? Let's analyze the data together. The initial discovery. The story begins with a technological marvel of planetary defense. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes better known as ATLAS, triggered an alert. This NASA-funded system, with University of Hawaii's Larry Deno as its principal investigator, scans the entire night sky every 24 hours. Its primary mission is to find near-Earth objects, but on this day, its algorithms flagged something extraordinary. The object's trajectory was hyperbolic, a clear mathematical signature indicating its velocity was far too great for it to be a member of our solar system. It was on a one-way ticket just passing through. The global astronomical community immediately mobilized, and within a day, the Minor Planet Center officially designated it 3Y Atlas, confirming it as just the third interstellar object ever detected. While early images showed the familiar coma and tail of a comet, its origin story was anything but familiar. This was an artifact from another star system, a rare opportunity that our technology, far more advanced than during the 2017 flyby of Oumuamua, was finally ready to seize. The anomalous frame. This is the moment a routine observation devolved into a profound enigma. The final frame broadcast from NASA's feed, captured at precisely 03:1712 UTC, initially seems unremarkable. The faint glow of the comet's nucleus, enveloped by its gaseous coma, is set against the cold vacuum of space. But in the lower left quadrant, a detail emerges that just violates the natural aesthetics of a comet. It's a glint of light, but it's not diffuse or scattered. It's a perfectly straight edge, a sharp, geometric line. Physicists identify this as specular reflection, the kind of clean bounce of light you get from a polished surface, not the chaotic scattering produced by a chunk of fractured ice and rock. This observation immediately brought to mind the work of researchers like Harvard's Avi Loeb and his Galileo project, which actively searches for extraterrestrial technosignatures. Independent analysts quickly ran the image through edge detection algorithms, which confirmed the anomaly, a line segment about 37 pixels long, presenting an angle and sharpness inconsistent with any known natural cometary phenomenon. The data pointed to a chilling possibility, that the light was reflecting off something manufactured. Data verification. In an age of digital manipulation, the first question is always, is the evidence authentic? This is where the power of modern data integrity and citizen science comes into play. Before any official statements were made, a global network of independent archivists had already secured the data. These individuals run automated scripts that continuously download and mirror raw data feeds from space agencies. Within minutes of the blackout, copies of the feed from Australia, Germany, and the United States were uploaded to public servers. Each file, carrying the identical 03:1712 UTC timestamp, was validated with a unique SHA-256 checksum. This cryptographic hash functions as an incorruptible digital fingerprint. Altering even a single pixel would result in a completely different hash. When every copy was compared, they were all identical. The chain of custody was flawless, from NASA's original relay to the decentralized archives. This rigorous process proved the anomalous frame was not a hoax or a transmission error. The data is immutable, the archives are clean, and the mystery, as the celebrated astronomer Carl Sagan often emphasized, is therefore deserving of serious scientific inquiry because the foundational evidence is verifiable by anyone. Technical explanations. If the data is real, could the blackout be a staggering coincidence? To answer that, we have to look at the technology involved. NASA's communications architecture is, a global machine. It relies on the Deep Space Network, or DSN, with its massive radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia. This system works in concert with the Tracking and Data Relay Satellite System, a constellation first launched in 1983, to provide continuous contact with probes and telescopes. Signal dropouts are a normal part of operations. As the Earth turns, a spacecraft will dip below the horizon of one DSN station, requiring a signal handover to the next. Sometimes this process, managed by engineers like JPL's Bradford Arnold, isn't perfectly seamless, causing a brief interruption known as a handover blank. These routine events are meticulously logged with specific reason codes. However, the outage at 0317 UTC, occurring at the exact second the anomaly was visible, did not have a standard handover code in the public logs. The official explanation cited general network instability, but the uncanny timing and lack of a specific technical fault code has left many experts and observers deeply unsatisfied. Digital forensics. Now let's zoom in to the pixel level, where the digital reality of the image is forged. Forensic analysis of the final frame revealed two critical clues that could point to a non-exotic explanation. First, the glint's straight edge aligns perfectly with the boundaries of several 8x8 pixel blocks. This is a telltale sign of how video compression algorithms like MPEG function. To reduce file size for transmission over vast distances, these codecs divide the image into a grid and can sometimes amplify or quantize a faint, noisy line into an unnaturally sharp, blocky one. The second clue involves cosmic rays. Deep space is saturated with high-energy particles that can strike a camera's sensor and overload a few pixels, creating a bright, transient streak that lasts for only a single frame. Digital forensics experts like Professor Hani Farid have documented how common these sensor-level events are in space imaging. Therefore, a leading theory proposes a double-hit scenario. A cosmic ray created a faint, linear artifact on the sensor, which was then exaggerated by the compression codec into the illusion of a perfect, solid edge. It's a plausible, purely technical explanation, though the brightness and consistency of the glint still push the boundaries of a typical artifact. 3i Atlas background. To truly grasp the significance of the anomaly, we must understand the object itself. Even before the controversial frame, 3i Atlas was a scientific puzzle. Detailed spectroscopic data from the James Webb Space Telescope, analyzed by teams including researchers like Martin Cordner at NASA's Goddard Space Flight Center, revealed a startling chemical composition. Unlike most comets from our own solar system's Oort cloud, such as the famous comet Hale-Bopp from 1997, which was rich in water ice, 3i Atlas was overwhelmingly dominated by carbon dioxide. It had a CO2 to water ratio of nearly 8:1. This means carbon dioxide ice, not water ice, was the primary fuel for its spectacular outgassing, creating a massive coma that stretched for hundreds of thousands of kilometers. This dense gaseous shroud completely hid the nucleus from direct view, with estimates placing its diameter at under a kilometer, comparable to the second interstellar visitor, 2I Borisov, which passed through in 2019. The Atlas survey's rapid scanning capability allowed for its early detection, giving us a precious opportunity to study it. This unique chemistry already confirmed it was an alien object, formed in a star system profoundly different from our own. Scientific scrutiny. In science, and especially in the search for extraterrestrial intelligence, skepticism is, well, the default position. Any extraordinary claim must survive a trial by fire. An anomalous signal in a single frame from one instrument is merely the starting point, not the conclusion. You see, the guiding principle is that extraordinary claims require extraordinary evidence. For the glint on 3i Atlas to be considered a credible techno-signature, it must be independently confirmed by other observatories using different instruments, preferably across multiple wavelengths of light. This is how science separates a true signal from instrumental noise or an artifact. As of now, the evidence remains on the lowest rung of this ladder of proof. We have a single, tantalizing data point, but no corroborating observations. Until the Hubble Space Telescope, the JWST or major ground-based observatories can produce matching data, the majority of the scientific community, including veteran SETI astronomers like Jill Tarter, will urge caution. It's a slow, rigorous process designed to ensure that when a discovery is announced, it is built on a foundation of undeniable, repeatable evidence, preventing the kind of historical misinterpretations like Percival Lowell's belief in Martian canals. 3 theories. The debate over the anomaly has coalesced into 3 competing hypotheses. The first is grounded in conventional cometary physics. Comets are chaotic bodies. The intense solar heating experienced by 3I Atlas could have caused thermal stress, fracturing the nucleus and cleaving off a large, flat shard of ice or rock. The unusual glint could be nothing more than a brief reflection of sunlight off this newly exposed, highly reflective surface. The second theory points to a technological illusion. This is the Occam's razor explanation, suggesting the edge is simply a convergence of unrelated phenomena. A cosmic ray striking the sensor at a shallow angle, its effect amplified and distorted by the video codec's blocky math. It's a ghost in the machine. But the third idea, the one that challenges our assumptions about the universe, refuses to be dismissed. This hypothesis, echoing the speculative work of physicists like the late Freeman Dyson, posits that the object is exactly what it appears to be, manufactured. Perhaps it's a component of a self-replicating von Neumann probe, a fragment of a light sail, or a piece of a protective shell. The odds are admittedly long, but the data is just ambiguous enough to keep the possibility on the table. Broader implications. An event like this, a mysterious signal followed by an unexplained data blackout, has consequences that extend far beyond the astronomical community. It becomes a catalyst for public debate and a driver of scientific policy. The conversation shifts from what is that object, to who controls the data and the narrative of discovery. It amplifies calls for greater transparency and the development of open-source data platforms, a principle that is driving next-generation projects like Chile's Vera C. Rubin Observatory. For the public, it's a powerful lesson in critical thinking, reminiscent of the global reaction to the famous 1977 WOW signal. That powerful, unexplained radio burst detected by astronomer Jerry Amon remains a cornerstone of SETI lore. This incident with 3I Atlas forces a conversation about our technological and psychological readiness for a potential first contact scenario. It challenges international bodies like the UN's Committee on the Peaceful Uses of Outer Space to consider protocols for such an event. It perfectly illustrates the tension between rigorous skepticism and the profound sense of wonder that fuels our exploration of the cosmos. The search continues. So, where does this leave the investigation? The official record is clear on a few facts. At 0317 UTC, the NASA feed was cut. The final frame contains a cryptographically verified geometric anomaly. The blackout's timing, while officially attributed to network issues, is highly suspect. As of today, no conclusive, peer-reviewed evidence exists to support an artificial origin for the glint on 3I Atlas. However, the search for answers is accelerating. Ambitious new missions are already in development, most notably the European Space Agency's Comet interceptor. Scheduled for launch around 2029, this innovative spacecraft will park itself at a stable Lagrange point in space, essentially lying in wait for the next long-period comet or interstellar visitor to arrive. It will then be deployed for a close-range flyby, giving us our first high-resolution look at one of these pristine objects. This proactive strategy, championed by scientists like the mission's lead, Geraint Jones, demonstrates a paradigm shift in how we study these cosmic messengers. Every interstellar visitor is a gift, pushing our technology and our theories to their limits. The strange case of 3I Atlas remains one of the most compelling technological mysteries of our time. Caught between a plausible digital artifact and a discovery that could reshape the future of humanity. The verified data presents an anomaly, but the ultimate explanation is still out there, traveling through the darkness of our solar system. What is your analysis? Was this a ghost in the machine, a 1 in a billion natural coincidence, or our first fleeting data point from a technology beyond our own? Share your hypothesis in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the technology that is shaping our future. Thanks for watching InnoVision Tech. What if I told you that in 2017 humanity received its first confirmed visitor from another star system, and we almost missed it completely? This mysterious object, traveling at 26 kilometers per second, defied every law of physics we thought we understood, accelerating away from the sun without any visible explanation. Here's the mind-blowing part. Some of the world's top scientists now believe we may have just witnessed our first encounter with alien technology. Did you know that Oumuamua is still the only confirmed interstellar object we've ever detected, and it's already gone forever? Oumuamua initial detection. On October 19, 2017, the universe delivered humanity its first confirmed interstellar messenger, and it caught us completely off guard. The Pan-STARRS telescope in Hawaii was conducting routine asteroid surveys when astronomers Robert Warwick and his team spotted something extraordinary streaking across the starfield at unprecedented velocity. This wasn't just another space rock cataloged in their database, it was moving too fast, coming from the wrong direction, and following a trajectory that immediately screamed outsider to anyone familiar with solar system dynamics. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, recognizing that this discovery would fundamentally change our understanding of what lurks in the spaces between stars. Within hours of the initial detection, telescopes around the world were frantically tracking this mysterious visitor as it hurtled past Earth at 26 kilometers per second, speeds that dwarfed anything gravitationally bound to our sun. The object had already completed its closest approach to our star and was racing toward the outer solar system, giving scientists only a precious few weeks to study it before it vanished forever into the cosmic void. What made this discovery truly groundbreaking wasn't just that Oumuamua came from another star system, it was the first interstellar object ever detected passing through our cosmic neighborhood, opening an entirely new field of astronomy and raising profound questions about what else might be drifting silently through the galaxy, undetected by our current observation methods. Classification challenges. The moment scientists began analyzing Oumuamua's properties in detail, they realized they were dealing with something that defied every classification system developed over centuries of astronomical observation. Initially tagged as Asteroid A/2017 U1 based on preliminary observations, the object quickly demonstrated characteristics that challenged this hasty designation. Unlike typical asteroids which maintain relatively stable brightness patterns as they rotate, Oumuamua's luminosity varied dramatically by a factor of 10 as it tumbled chaotically through space, suggesting an extremely unusual elongated shape that was unprecedented in solar system astronomy. Even more puzzling, despite approaching within 0.25 astronomical units of the Sun, close enough to vaporize surface materials on most comets, it displayed absolutely no coma, tail, or any other signs of outgassing that should accompany such solar heating. NASA's Jet Propulsion Laboratory and international astronomy teams spent months in heated debates, frantically analyzing spectroscopic data and photometric measurements while flip-flopping between asteroid and comet classifications as new observations contradicted previous assumptions. The confusion reached such levels that by 2018, the International Astronomical Union was forced to create an entirely new category, officially designating it 1I/Oumuamua, the 1I indicating the first confirmed interstellar object, and establishing a new nomenclature system for future discoveries. This classification nightmare highlighted how woefully unprepared our taxonomic systems were for objects originating beyond our solar system, forcing the scientific community to acknowledge that Oumuamua might represent a completely unknown class of celestial bodies formed under conditions and processes entirely different from anything occurring within our sun's gravitational influence. Trajectory analysis. When astronomers reverse-engineered Oumuamua's cosmic journey using sophisticated orbital mechanics calculations, they uncovered an epic tale spanning potentially millions of years across the vast emptiness of interstellar space. The comprehensive trajectory analysis performed by international teams at ESA's European Space Operations Center and NASA's Jet Propulsion Laboratory revealed that this interstellar wanderer had been drifting through the galaxy long before our solar system had even settled into its current configuration of planets and orbital resonances. Using precise astrometric measurements from multiple observatories, researchers initially calculated that tracing its path backward pointed toward the direction of Vega in the constellation Lyra, one of the brightest stars in our night sky. However, deeper analysis incorporating proper motion corrections and galactic rotation models revealed a far more complex story that challenged simple origin theories. The object would have needed approximately 600,000 years to travel from Vega's current position to reach our solar system, yet stellar motion calculations proved that Vega wasn't located in that position 600 millennia ago due to the constant movement of stars through galactic space. This startling discovery proved that Oumuamua was a true galactic nomad with no clear stellar home, having wandered through multiple stellar neighborhoods during its cosmic odyssey. Its hyperbolic trajectory, a mathematically defined path that curves around the Sun once before heading back to interstellar space forever, indicated approach speeds of 44 kilometers per second relative to our Sun at perihelion. Unlike the elliptical orbits of comets and asteroids gravitationally bound to our star, Oumuamua possessed more than enough kinetic energy to escape permanently into the cosmic wilderness, never to return to our solar system again. Photometry and shape analysis. The light measurements of Oumuamua revealed, honestly, the most bizarre shape ever recorded for any natural object in our solar system. Photometric observations conducted by observatories all over the globe, including the Very Large Telescope in Chile and Gemini Observatory in Hawaii, showed brightness variations that, well, could only be explained by an extremely elongated form. Scientists calculated that Oumuamua was at least 10 times longer than it was wide, with dimensions roughly 400 meters by 40 meters, kind of resembling a cosmic cigar tumbling end over end through space. Dr. Karen Meach from the University of Hawaii led international teams analyzing these light curves, discovering the object completed one full rotation every 7.3 hours. The extreme aspect ratio was totally unprecedented. No known asteroid or comet even came close to such proportions. Some researchers, including Dr. Shmuel Bieli, proposed it might be even flatter, resembling a cosmic pancake rather than a cigar, which, honestly, would make it even more unusual. The surface appeared reddish, similar to objects in the outer solar system that have been darkened by cosmic radiation over billions of years. However, Oumuamua reflected only about 4% of incident sunlight, making it darker than charcoal. This combination of extreme elongation, dark surface, and rapid tumbling motion created a unique signature that really challenged existing models of how small bodies form and evolve in space, suggesting formation processes completely unlike anything occurring in our solar system. Acceleration anomaly. The discovery that, honestly, shattered every conventional explanation came when precise tracking revealed Oumuamua was accelerating away from the Sun in ways that just defied physics. Dr. Marco Michelli and his international team published their groundbreaking findings in Nature journal in June 2018, documenting a small but measurable non-gravitational acceleration of approximately 4.92 times 10 to the minus 6 meters per second squared. This wasn't measurement error. Multiple independent observations confirmed that Oumuamua was actually speeding up as it moved away from our star. For typical comets, acceleration like this makes perfect sense. Frozen gases sublimate near the Sun, creating jets that act like tiny rocket engines. However, Oumuamua showed absolutely no signs of this outgassing activity. No visible coma, no tail, no gas emissions detectable by any instrument. The Hubble Space Telescope conducted follow-up observations that confirmed the anomalous motion while ruling out systematic errors or unknown forces. This acceleration was too large to be explained by solar radiation pressure alone, yet too small to be caused by gravitational influences from planets or other bodies. The mystery deepened when scientists realized that whatever was causing this acceleration appeared to be acting continuously and smoothly, rather than in bursts typical of comet outgassing. This unprecedented behavior forced astronomers to consider possibilities they had never seriously contemplated. Either Oumuamua represented a completely unknown type of natural phenomenon, or, well, something artificial was responsible for its strange motion through our solar system. Spitzer observations. NASA's Spitzer Space Telescope conducted humanity's final attempt to solve the Oumuamua mystery before the object disappeared forever beyond the reach of Earth's instruments. During November 2017, this infrared observatory pushed its capabilities to the absolute limit, conducting some of the most sensitive thermal measurements ever attempted on such a distant small object. Dr. Davide Farnochia and his team at JPL analyzed the resulting data, hoping to detect the warm signatures of outgassing that might explain the acceleration anomaly. Instead, Spitzer's observations only deepened the puzzle. The telescope detected virtually no thermal emission from Oumuamua, setting strict upper limits on any dust or gas production. If the object were behaving like a normal comet, even minimal outgassing should have created detectable infrared signatures, as solar heating warmed expelled material. The absence of such emissions meant that if outgassing was responsible for the acceleration, it had to be composed of materials completely invisible to infrared detection. Spitzer's measurements also refined estimates of Oumuamua's size and reflectivity, suggesting it was smaller than initially calculated, possibly only 100 to 200 meters in its longest dimension. This smaller size would actually amplify any outgassing effects, making the lack of detectable emissions even more mysterious. The final Spitzer observations in January 2018 showed Oumuamua continuing its anomalous acceleration while remaining thermally invisible, leading scientists to conclude that conventional comet behavior could not explain this object's properties and motion through our solar system. Artificial origin hypothesis. When every natural explanation failed, Harvard University's Professor Avi Loeb and postdoctoral researcher Shmuel Bialy proposed the unthinkable in a paper published in the Astrophysical Journal Letters in October 2018. They suggested that Oumuamua might actually be artificial, specifically a light sail created by an extraterrestrial civilization. This hypothesis, honestly, elegantly explained the acceleration anomaly. A thin, flat object could be pushed by solar radiation pressure without requiring any outgassing. For this mechanism to work, Oumuamua would need to be incredibly thin, less than 1 millimeter thick, while still maintaining its observed dimensions. Loeb proposed it could be debris from alien technology, possibly millions of years old, just drifting through space like cosmic junk from a long-dead civilization. The light sail hypothesis explained not only the non-gravitational acceleration, but also the object's extreme elongation and its unusual tumbling motion. Dr. Loeb argued that extraordinary claims require extraordinary evidence, but, extraordinary evidence also requires extraordinary hypotheses. The scientific establishment reacted with fierce criticism, with many astronomers arguing that invoking alien technology violated Occam's razor, the principle favoring simpler explanations. However, supporters pointed out that dismissing the possibility without proper investigation could actually represent a form of cosmic prejudice. The debate raged across scientific journals and conferences, with researchers split between those demanding more conventional explanations and others willing to consider that humanity had encountered its first piece of alien technology, even if we couldn't definitively prove it. Dark comet theory. Dr. Daryl Seligman from the University of Chicago proposed a revolutionary alternative that really challenged our understanding of comet composition and interstellar chemistry. The dark comet hypothesis, which was published in the Astrophysical Journal back in 2020, suggested that Oumuamua could actually be made mostly of frozen molecular hydrogen. In the extreme cold of interstellar space, where temperatures are around 14 Kelvin, hydrogen can freeze into solid ice that would stay stable for millions of years. As Oumuamua got closer to our sun, this hydrogen ice would sublimate directly into gas, but unlike water vapor or other typical comet materials, hydrogen gas is almost completely invisible to most astronomical instruments. This invisible outgassing could explain the mysterious acceleration without creating any visible coma or tail. The theory goes on to suggest that Oumuamua formed billions of years ago in a giant molecular cloud. Those vast regions of space where gas and dust come together before forming new stars and planetary systems. These environments could create really unique conditions for hydrogen ice to build up, making objects unlike anything we've seen in our own solar system. Seligman's calculations showed that a hydrogen iceberg about the size of Oumuamua could stay intact during its journey through interstellar space, and provide enough outgassing to explain the observed acceleration. This hypothesis opened up the possibility of an entirely new class of interstellar objects that might be drifting undetected all over the galaxy, basically invisible to our current observation methods, because their outgassing doesn't produce any visible signatures that our telescopes can pick up. Dark comet classification. The implications of the dark comet theory went way beyond just Oumuamua. It could totally revolutionize the way astronomers classify small bodies in space. Researchers at NASA's Jet Propulsion Laboratory started developing new classification systems to account for objects that show non-gravitational acceleration, but without any visible activity. Scientists began to propose distinguishing between small dark comets like Oumuamua, which came from interstellar space, and potentially large dark comets that might actually exist within our own solar system, just unrecognized up until now. Dr. Daryl Seligman and his colleagues even identified several objects in the solar system database that showed unexplained acceleration without obvious outgassing, suggesting that dark comets might be way more common than we ever imagined. The new classification parameters included things like thermal emission signatures, spectroscopic properties, and acceleration magnitudes that are really different from what we see with traditional comets and asteroids. This new framework suggested that maybe our telescopes have been missing a whole population of hydrogen-rich objects simply because our detection methods are tuned for water-ice comets and rocky asteroids. The European Space Agency even started to include dark comet detection protocols in their future mission planning, realizing that interstellar visitors could be a lot more common than just the single confirmed case of Oumuamua. Some researchers estimated that if the dark comet hypothesis is correct, the galaxy could have billions of these invisible objects, creating a hidden population of interstellar wanderers that occasionally pass through planetary systems without us even noticing. This whole idea really changes our understanding of how material is distributed across the galaxy, and it suggests that the space between stars could be way more crowded with small bodies than our astronomical models had predicted. Scientific debate. The Oumuamua controversy has basically split the astronomical community into competing camps, each one defending some pretty radically different interpretations of the same data. Team Natural, led by researchers at NASA's Goddard Space Flight Center and the European Southern Observatory, insists that conventional physics has to explain the acceleration anomaly, and they propose things like outgassing of common volatiles or internal changes during solar heating. Then there's Team Artificial, led by Harvard's Avi Loeb and backed by researchers from Tel Aviv University, who argue that the light sail hypothesis deserves serious scientific consideration, and shouldn't just be dismissed because people are skeptical about extraterrestrial explanations. Team Dark Comet, centered around researchers at the University of Chicago and Yale University, is pushing the hydrogen iceberg theory and working on ways to detect similar objects. The debate has been going strong in top scientific journals like Nature, Science, and the Astrophysical Journal since 2018, and honestly, each new analysis seems to make the mystery even deeper. Dr. Alan Fitzsimmons from Queen's University Belfast leads the skeptics, saying that these exotic explanations go against scientific principles, while Dr. Abraham Loeb's supporters counter that extraordinary evidence demands extraordinary hypotheses. Recent studies have even found more solar system objects with similar properties, which could support the dark comet classification. The scientific process is working exactly as it should. Competing hypotheses are driving new observations and new theories. Whether Oumuamua was natural, artificial, or something totally unprecedented, it's already changed astronomy by showing that interstellar objects can really challenge our most basic assumptions about the universe, forcing scientists to broaden their frameworks for understanding cosmic phenomena. So, there you have it. Oumuamua is still one of the greatest mysteries in modern astronomy, challenging just about everything we thought we knew about interstellar objects. Whether it was a natural dark comet, alien technology, or something completely unprecedented, this cosmic visitor has forever changed the way we see our place in the universe. What's your theory? Was Oumuamua our first glimpse of extraterrestrial engineering, or does nature still have more surprises up its sleeve? Drop your thoughts in the comments below. I read every single one. And if you're fascinated by these mind-bending space mysteries, go ahead and smash that subscribe button and hit the bell icon so you never miss the latest discoveries from InnoVision Tech. Until next time, keep looking up. There are images that show us beauty, and there are images that show us truth. This one does neither. At first glance, it looked like a failure, a photograph that refused to focus, but behind that blur was something extraordinary. The third interstellar object ever observed, 3I, Atlas, currently racing through our solar system. What does this mysterious image actually reveal? What secrets are hidden in the data that our eyes can't see? Let's explore this together. How do you photograph something that refuses to stay still? Capturing 3I Atlas wasn't like shooting an ordinary comet. It moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects a few seconds of light, the object has already traveled thousands of kilometers, moving at a blistering speed of roughly 12 kilometers per second relative to the sun. A single frame would show nothing but a soft, meaningless streak. To overcome that, as orbital dynamics expert Davide Farnocchia can attest, the telescope had to chase it. Tracking software predicted the comet's path second by second, adjusting the mount in near real time to keep the magnitude 17 object perfectly centered on the sensor. For context, that is over 25,000 times fainter than the faintest star visible to the naked eye. As a result, the stars in the background blurred into trails, but 3i Atlas held its position. What looks like a still blur in the final image is actually motion perfectly cancelled out. The challenge is immense. Even a tiny error in the predicted trajectory would smear the object into invisibility. This wasn't just a photo, it was time made visible, a precise balance between the comet's impossible speed and the telescope's relentless pursuit, a feat of engineering that astronomers at the Minor Planet Center work to perfect daily. What do you do when an object's shape is also its shadow? In the image, 3i Atlas doesn't show a surface. There's no crisp edge, no nucleus shining at the center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself. The elongation is unmistakable, smooth at one end, uneven at the other, with a length-to-width ratio estimated to be at least 3:1. This shape has puzzled everyone studying it, including specialists in cometary structure like Karen Meach, whose work on 1i Oumuamua set the precedent for analyzing such faint signals. If it were a normal comet, we'd expect a rounded head and a tapering tail. This is different. The frame shows a body that seems evenly stretched, almost like a cylinder. The brightness peaks slightly toward one side, suggesting it might be spinning rapidly on a 7 to 9 hour rotation period, blurring its features the way a long shutter smooths moving water. The faint light we see isn't emission, it's reflection scattered through a thin layer of ejected material, too tenuous to be called a proper coma. This object's form is defined more by its interaction with light than by its physical boundaries. The shape stands as a physical clue wrapped in uncertainty geometry without a surface. What can a lack of color tell us about an object's past? When astronomers processed the raw images of 3i Atlas, they found something curious: no real color. Most comets show at least a hint of tone, like a greenish halo from cyanogen gas. But this object gives almost nothing. Across visible wavelengths from 400 to 900 nanometers, its spectrum flattens into a neutral gray. As planetary scientist Alan Fitzsimmons has explained with similar objects, this absence tells us 3i Atlas isn't actively outgassing in any strong way. Instead, we are seeing pure reflection bouncing off a surface so dark it has an albedo, or reflectivity, of only 2 to 3%, literally blacker than asphalt. Over millions of years drifting between stars, its surface has been bombarded by cosmic rays, baking carbon molecules into complex dark organics called tholins. These materials absorb almost every wavelength of light, combining into a neutral gray when seen from a distance. A slight rise in the infrared spectrum suggests the presence of carbon dioxide ice just below the crust, but the signal is incredibly weak. For an interstellar object, that lack of vibrancy isn't emptiness. It's age, a testament to an eons-long journey through the void. This is the color of endurance. So, how do you prove something exists when it's barely even there? That's the puzzle with 3i Atlas. It lives right on the edge of what our detectors can actually prove. In its raw data, the comet is like a whisper above the background noise, with a signal-to-noise ratio just barely clearing the 3 sigma statistical threshold that's required for a confirmed detection. But, as astronomer David Jewett, a pioneer in discovering faint objects in the Kuiper belt, would confirm, the difference between random static and a real object is consistency. Real light behaves with intent. It repeats and holds a pattern where chaos simply can't. That's what makes the 3i Atlas image meaningful. Across exposures, the faint streak appears in the exact same coordinates predicted by orbital models, delivering just a few dozen photons per minute to the detector. Its brightness curve remains stable despite atmospheric shifts and thermal noise from the camera itself. The data isn't just faint, it's fragile, requiring mathematical reconstruction to separate the comet's photons from random ones. This process, called image stacking, is less like taking a picture and more like building one from scratch over hours of observation. The final image exists only after millions of calculations reduce chaos into geometry. It's an image at the threshold of certainty, not sharp enough for comfort but too consistent to dismiss. What happens when your discovery refuses to be discovered? Once the image of 3I Atlas was assembled, it didn't behave like anything the calibration software was designed for. Algorithms that measure coma, nucleus, and tail couldn't settle on a pattern. The numbers diverged. In data terms, that means the target is either unstable, or the physics behind it doesn't fit our templates. As interstellar object expert Matthew Knight has noted in his research, these visitors often challenge our models. 3I Atlas breaks the logic. Its confirmed hyperbolic orbit, with an eccentricity of roughly 1.1, proves it's not from around here. It behaves like something between 1I, Oumuamua, which had no visible coma, and 2I, Borisov, which displayed a textbook coma even at 3 AU from the Sun. Its blur is too diffuse to be a solid asteroid, but too clean to be an active comet. That ambiguity makes classification nearly impossible using standard cometary models. The picture isn't wrong, it's just showing us a kind of object our instruments and our scientific language weren't built to categorize. It exists in a scientific gray area. When an image can't explain itself, how do you make it talk? Mathematics takes over. The frame of 3I Atlas is too faint for traditional analysis, so scientists like Robert Warwick, the discoverer of Oumuamua, turned to numbers to extract what the light couldn't say. Every pixel becomes a coordinate, every shade of gray a probability. The first step is motion modeling through precise astrometry. Plotting its position across nights confirms its hyperbolic trajectory and its 12 kilometers per second velocity. The math is certain, it's moving too fast to ever be captured by our sun. Next comes brightness fitting, or photometry. The faint gradient along its length is modeled to estimate its shape and rotation. Simulations show that if the nucleus is elongated with a 3-to-1 ratio, a slow tumble could recreate the uneven brightness we see. The math detects a tiny variation the eye can't. Even the blur itself becomes measurable through a process called deconvolution, which mathematically reverses the distortions, separating motion blur from its intrinsic shape. The image shows uncertainty, but the equations describe exactly why it must look that way. Is that a real shape, or just a ghost in the machine? Every astronomical image has them. Cosmic rays can leave small flares, and tiny tracking errors can accumulate and masquerade as structure. When the first image of 3I Atlas was released, that question appeared immediately. How much is the comet, and how much is the instrument? The cylindrical blur could, in part, be a subtle elongation caused by the camera compensating for motion and noise, an effect related to the telescope's point spread function. A residual drift of just half a pixel per exposure, when multiplied by dozens of frames, creates a false extension. But not all anomalies vanish under scrutiny. As astronomer Wesley Fraser has explored in his work, consistency is key. When the images were independently processed using different software, the same general elongation remained. The angle of tilt and brightness gradient persisted. That argues against coincidence. If distortion were the only cause, its signature would shift between instruments or processing techniques. Instead, the shape repeated itself, asserting its bizarre geometry through the limits of our observation. At some point, what do you call something that refuses to be named? The discussion around 3I Atlas stopped being about what it looked like and became about what it refused to be. It wasn't a traditional comet, lacking a tail. It wasn't an asteroid. Its light curve was just too smooth and its spectrum way too neutral. It presented something in between, a blur that really resisted interpretation. The data which experts like Amy Mainzer from NASA's NEOWISE mission used to classify thousands of small bodies paints a picture of contradiction. The brightness curve, varying by less than 10%, suggests a single, stable body, yet its slight asymmetry hints at a slow tumble, or maybe even fragments orbiting a shared center. Its trajectory confirms an interstellar origin, a path that ensures it will never return. That certainty of escape is, honestly, the only familiar thing about it. It forces us to confront the uncomfortable idea that seeing isn't the same as knowing. Sometimes, the clearest image possible is one that stubbornly refuses to resolve. It challenges not just our technology, but our very system of classification. So, if it defies every category we have, what could it be? This is where scientific observation meets informed imagination. 3. I Atlas sits perfectly between the two prior interstellar visitors. 1 I, Oumuamua, was sharp and fast. 2 I Borisov was almost too typical. 3 I Atlas is neither, behaving like a memory of both. It's too diffuse to be solid rock, too clean to be a classic comet. It exists in a gap where our definitions just totally fail. It's objects like this that inspire radical new ideas. When data stops fitting patterns, thinkers like Avi Loeb have argued that we must be open to unconventional explanations. While he was referring to Oumuamua, the principle really applies here. Is this a new type of dark comet that outgasses materials our instruments can't detect? Could it be a fragment from a tidally disrupted exoplanet, an entirely different class of object? Is it 90% asteroid and 10% comet? Or something else entirely? The object is a scientific mystery box. The blur is both evidence and absence, a confirmed detection that withholds its identity, reminding us that our categories are only conveniences, not cosmic truths. What is the final story of a visitor we only glimpse as it leaves forever? When the light from 3 I Atlas fades from our view, the photograph will remain, a faint smear in an archive. In most sciences, this would be dismissed as inconclusive. In astronomy, it becomes the most honest evidence possible. As astrophysicist Gregory Laughlin might agree, a blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about 3 I Atlas, its speed, its path, its rotation, its chemical hints, exists inside that faint streak. Its weakness is its strength. It forces meaning to come from physics and mathematics rather than from simple appearance. Soon, it will leave our system entirely, receding back into the interstellar dark. The blur we have is not the beginning of a study but the end of accessibility. It's not a picture of a destination, it's a snapshot of passage. It is a faint fingerprint left on the window of our solar system by a traveler just passing through. 3 I Atlas was never truly seen. It was measured by its blur, and that is the clearest image we could ever hope for. Three. I Atlas is a visitor that escapes our definitions, a blur that exists in the thin space between what we know and what we can only imagine. What do you think is hiding within that faint smear of light? Share your theories in the comments section below. We're always curious to hear what you think. If you want to continue exploring the universe's greatest unsolved puzzles with us, don't forget to like, subscribe, and hit the bell icon so you won't miss our next deep dive. Thank you for watching InnoVision Tech.